It's not very far-fetched to imagine a world in which the dominant mode of interaction is that AI talks to other AI systems. We've delegated our wishes, our goals, our plans to AI, but it's also pursuing them by interacting with other AI systems which have other goals delegated to them. The models then conspire to solve the problem in a way that they're their own devising. What that affords is an opportunity for the outcome to deviate very significantly from what the humans might have wanted in the first place.
Dr. Chris Summerfield is a neuroscientist, AI researcher, and cognitive science professor at Oxford University, whose work has transformed how we understand intelligence, both in humans and machines. He spent decades studying how the brain predicts, perceives, and decides, revealing the hidden algorithms behind consciousness and cognition. As an early contributor at DeepMind with Nobel Prize winner Demis Hassabis, Chris now sits at the cutting edge of neuroscience-inspired AI. He's also the author of These Strange New Minds, a bold exploration of whether machines like ChatGPT are starting to think and what that tells us about ourselves. Subscribe if you want to know why your brain is basically doing autocomplete on reality and why AI might be already doing the same.
I have a good friend and colleague who's built a foundation model for psychology. So the idea is lots and lots of psychology data, so sort of rows of descriptions of experiments and then results, and trained it on many millions of rows of data. Then you could feed in a new experiment and it can predict what people are going to do, even if you haven't run that experiment yet.
It's so weird. That's so strange. You've been at the forefront of AI for a number of decades now. What's really surprised you about the last couple of years where we've just seen a complete explosion in AI commercialization, technology, and everything?
Everything. The short and the long answer. Yeah. I mean, where to start, right? So, I guess that if you want to take a potted history of the last couple of decades, there's this thing called deep learning. Deep learning it began as one branch of AI, a branch in which essentially you take simulated networks of neurons with lots of parameters, and you adjust those parameters to get the network to learn something from scratch. That approach it was first invented in the 60s. It went in and out of fashion for a while. In the early 2000s, it was at this sort of nadir of deep unfashionableness. And then a few people came along and started to revive. There was a sort of constellation of kind of happy coincidences, some technical advances, increasing computer power, and so on. Deep learning took off, and everyone was like, okay, the pendulum has just swung back from deep learning being unfashionable to deep learning being fashionable. Great. But I don't think anyone really anticipated that it would become not just the main event, but the whole deal.
Right. Okay.
So let me tell you the single thing that is the most astonishing to me. So obviously, deep learning today is all about language. I mean, not just language, but it's all about language. And the big step change is that nobody really thought that we would be able to use deep learning on its own to basically to build systems that can generate language in the same way that humans can. And of course, kind of what happened starting around about 2019, although it didn't really hit the mainstream until 2022, was that we got really good at doing exactly that. And I think the most astonishing thing is kind of a weird thing to say, but the most astonishing thing is that we were able to train systems that can generate language from language alone. That is the astonishing thing. Because although it sounds obvious, of course, if you want to be good at language, you need to be exposed to lots of language. That's just duh, right? But in 2019, it wasn't obvious. Almost everyone, including myself at that time, I think, thought that if you wanted to train a system, a deep learning system, to be able to generate language, it would also need to have access to all the other sorts of information that we, humans, have when we learn to generate language. It would need to be able to have vision, and it would need to be able to sense the world. Maybe it would need to understand social relations and how objects move around and all that kind of stuff.
Interesting.
People thought that was absolutely non-negotiable, and then it turned out not to be essential at all. And that was really shocking.
Very cool. do you think part of why that was so surprising is that no one had really thought about this solution to just throwing huge amounts of data and scaling up, data centers, and just throwing, orders of magnitude more compute at the problem?
People
Is
did.
that
People did think that people had
okay?
thought of that, but they thought that language was special, right? They
Okay.
thought that language was special because language is like our way of sharing reality with each other. And it's like so rich and so intimate for people, right? So, you think of the descriptions that you can make of like your experiences in life. Those descriptions are made in language, but they reference this much richer sensory world, which is full of colors and sounds and people and emotions and like all this kind of richness. And I think people just kind of thought that somehow language carried all that information because the language was produced by systems that were able to sense those types of things or experience those emotions, for example.
Right.
And that was just wrong.
Was that a sad moment for you in that realization that you were able to just throw data at the problem and make really good language systems? Was that sort of like a thing that you maybe weren't too happy to have come to fruition? You wanted it to be more of a human element, and you wanted the emotion and all the other things that come along with it?
So I personally don't feel like that, but many people do. Right?
Right.
I think many people kind of like they regret the kind of incursion of deep learning systems into provinces of cognitive behavior that were previously exclusively human. And actually, there are like powerful kind of like movements that are sort of partly scientific or technical and partly political that kind of like together sort of reject AI both as like both rejecting its capability and saying it's not as good as people say it is,
Yeah.
or really is, and kind of reject it, practically by saying, well, we shouldn't use it because it's like bad for people. And I think that in part those beliefs are driven by a desire, a very kind of reasonable and natural desire to like want to kind of ring fence certain things as being like, look, this is about people, this is special.
Yes. Yeah, and you have to have sympathy for the different areas that are going to be completely overturned, and we'll get into that later. What, for people that maybe aren't fully clear, what are the differences between how the brain produces language and how a language model produces language? Are there fundamental mechanistic differences?
Well, we don't know a lot about how the brain produces language, to be completely honest. And like, one of the reasons for that is that there is only one species that produces language. There's lots of species that communicate, but there's only one species that produces language, and that's us, humans. And when it comes to neuroscience, the tools that we have available for investigating the brains of humans are very crude
Right.
compared to the tools that we have for investigating, say, the brains of rodents. So rodent researchers these days can do these like insane things where they can like record simultaneously from tens of thousands of neurons, selectively inactivate some of them, and like work out what influence this has on the others and on behavior. It's like absolutely breathtaking what can be done, for example, in rodent neuroscience these days. But that's no good for studying language because mice don't give speeches. So
Right.
um, human language, the neuroscience of human language has always been it's been a challenge, it's been a challenging endeavor to understand that. And we know which parts of the brain are involved, and we thought we knew something about, kind of like different representations of things like nouns and verbs, but basically we didn't know at all how, and we still don't, how humans generate language. And in fact, the advent of language models, probably has taught us more about, it's taught, probably controversial to say it's taught us more about human language than everything else that went on before. I don't know if that's really a defensible statement, but it's done something really important, which is it's given us a proof for how it could work
Right.
because we've been able to build it.
What about the way the brain stores language, which I think is almost equally important to how it generates it? The way the brain stores language compared to a language model stores the language, stores the concepts,
Yeah.
stores concepts that are closer together closer together in the brain? Like, are there some similarities there?
Yeah. So let me start with the differences. So the differences is that when you experience language, so we're talking right now, but I have my eyes open. So what that means is that and my ears as well. So it means that there is more information that's coming into my brain than just the language that, kind of like what you're saying to me, essentially. So our experience of language is almost always inevitably multimodal. Like that's true for almost everyone. Depends. Some people have impairments that mean that's less true, but like it's true for almost everyone. So what that means is that the representations of like linguistic concepts in the brain, they are sort of like enmeshed with representations of perceptual concepts. So what that means is that there are parts of the brain where you would encode like, the brain knows what a horse looks like. For example, it knows that horses are similar to donkeys in terms of the fact that, they kind of look the same. And then there's another like nearby part of the brain that knows that, for example, the word horse is similar to the word like Morse, right? Because they share kind of like orthography and phonetics and so on. So in the human brain, those kind of go together. In language models, at least in sort of straight up language models trained from text, that's obviously not the case because they don't have the sort of visual input that we have. Now, today's language models or frontier AI systems are multimodal, so they will have, so that's maybe more true. But it's nevertheless a difference. Like the models do not sense the world in the way that we do in this sort of dynamic stream of like rich sensory information. So that's going to mean their representations are very different. That being said, there are striking commonalities too. So let me tell you about just two of them. So one is that in like parts of the brain which are relatively far from the sensory periphery, so that means that they're bits of the brain to which signals arrive after they've been processed quite a lot already. These bits will contain representations which are really, really abstract. So they'll represent things like the concept of Christmas. So Christmas is like, it's kind of a weird concept. So first of all, it's like a cultural festival, or cultural phenomenon. So it's like, kind of associated with a set of objects and practices and music and like, kind of like ways of greeting each other, all kinds of things that look nothing like each other, right? So a Christmas tree doesn't look anything like a sledge, but right. You'd know that they kind of go together in like, Christmas iconography or whatever. And so you'll find neurons deep in the human brain that care about things that are related to one kind of theme, like Christmas related things. If you examine the units in large language models trained just from text, then you will actually find things that are really quite similar. So you will find the emergence of like units, or it's more like small patterns, like patterns of neurons, but it doesn't matter. Patterns of neurons that seem to reflect like, kind of abstract concepts like, like Christmas. So that's one similarity. Both learn really useful abstractions that are very, very far from like shared sensory properties. The second thing is like language is, of course, not just about semantics, it's about syntax. So language has a structure. Sentences, there are valid sentences and there are invalid sentences, and you would detect very quickly if I said something that was like syntactically invalid, even if my words all kind of like broadly made sense. And like there are different ways in which we can understand how syntax is represented, but one of them is that, painstakingly linguists have tried to like divine what the rules are for syntax by creating trees of like legal sort of parts of speech and what can legally follow each other. And that basically translates to a sort of like hierarchy of like, legal rules for parts of speech, and you can represent it as this tree. So what you can also do is you can go into large language models, but nobody's ever taught them syntax, and you can look at their representations, and you can see that in a somewhat oblique ways, the representations in these models obey these syntactic trees. And so it's almost as if, like just by looking at the statistics of language, the models have somehow implicitly learned these syntactic rules, which linguists have studied for, decades and painstakingly delineated.
Right. Very cool. Very well explained. I love it. Science misinformation has never been higher, and the reason I started this channel is to combat that. With health influencers both giving health advice and selling health products, it's more important than ever to understand the basis of their scientific claims, because some will have very strong scientific backing and others just simply won't. That's why I've been a daily user of Consensus.ai for over a year now. Think of Consensus as the ChatGPT for science. It's a large language model similar to ChatGPT, but it's been trained specifically on research papers. There's been a lot of buzz lately online about creatine, so let's see what the consensus is. Does creatine help you build muscle? So at the top you have a consensus meter, which is taking results from 16 relevant papers. It says yes, 100%. Creatine supplementation is widely studied for its effects on muscle building. Great. The main reason that I really love Consensus is that it takes these papers that are very hard to read for pretty much anyone, me included, people with scientific training. They're just written poorly, and it breaks it down into very simple language with categories that are most relevant to the question. So effects on muscle mass and strength, mechanisms of action, magnitude of muscle growth, safety and recommendations, and conclusion. These are absolutely the perfect headings that are related to this question, and it sources every single claim that is made. You might be asking yourself, then why would I not just use ChatGPT? And the main reason is that it's been trained on a whole bunch of incorrect science, which means that I very frequently get outputs that I know to be incorrect, and especially in fields that are contentious or not completely proven, like basically all of brain science. The absolute best part is that Consensus are offering 1 full year of Consensus Premium completely free to my viewers. All you have to do is use the code The Giant Shoulder at checkout. That's a subscription that usually costs over $100, completely free, no cost, no harm in trying it out. Just use the code The Giant Shoulder at checkout. Really, everyone could do better at verifying the information that they receive, and there's no better tool than Consensus for that. I'm so curious, at the early points in your career, was there a spark toward, why did you go, you were on this brain sciences path. Why did you go towards computation and AI versus, wet lab, just boring old pipetting into beakers and wells and, what would be more typical of a neuroscience practice, probably 20 years ago, 30 years ago? What was it that pushed you in the direction of computational neuroscience, Neuro-AI?
Yeah, well, so my research group in Oxford still investigates the human brain using the techniques that are available to investigate the human brain, which is like large scale, but like brain imaging methods, so functional magnetic resonance imaging, fMRI. We were doing that back, kind of 15 years ago. We're still doing it to some extent today. But the answer to your question is serendipity. So I've been working on I've been interested in computation for a long time, and the reason is that computation provides like a language, it provides like a quantitative language for being really precise about how you think the brain works, right? So, rather than just writing a verbal description of like what the result of your experiment is, you can like write down a model. It's like a formal description of the way that information is transformed, and like you can use that as a kind of like a comparandum for like whatever you observe in your experiment. So you can say, to what extent are the processes in my model similar to the processes in the brain? So I've been doing that for a long time, but in a very kind of like very nuts and bolts sort of academic kind of way, unrelated to computer science at all. And then in 2010 I got a call from a friend who I knew from my neuroscience PhD, who said he was founding a startup that was going to work on AI, and did I want to be involved? And I didn't know anything about AI whatsoever, but I liked this friend, so I was like, sure, count me in. And I went along to some meetings, and I was like, wow, these people have like a vision, and their vision was to build AI by kind of like understanding the human brain through neuroscience, and then to use that as inspiration for building, really advanced AI. This was in 2010. So, as we're sort of, the pendulum is just about to swing from unfashionable to fashionable in the world of learning. And so, so I got on board and I got involved, and that company, that startup, chose a name. It chose to call itself DeepMind. And my friend was Demis Hassabis, who's, kind of like now Sir Demis Hassabis, who
Nobel Prize winner.
Nobel Prize winner for all his many achievements. And
Yes.
so I was like super lucky to have met Demis during my PhD. And I was super lucky to get involved early on. And that sort of gave me an opportunity to kind of see how this revolution happened. So I feel immensely privileged, and it totally transformed the way that I think about the brain. It totally transformed my career in terms of like my interests and, what I work on now. So yeah, but it was all just kind of like happenstance. I would never have done that by myself.
Wow. Such a cool story, and it has so much power now with what DeepMind has gone on to do. Demis Hassabis winning the Nobel Prize, breaking the protein code, beating the first player in Go with like what they've gone on to do as a company is just groundbreaking. And if anyone hasn't seen the AlphaGo documentary, it's one of my favorite things. As just a huge nerd of strategy games, but also just advancement in technology, I think it's just stunning. I am. What is the field of neuro-AI attempting to do? How does AI push neuroscience forward and vice versa?
Yeah, so there's been a lot of discussion about that and about, kind of the relative merits of, incorporating techniques from AI into neuroscience. So yeah, let me begin by just defining what it is. So Neuro-AI is a field, it's a subfield of neuroscience, although a pretty big subfield of neuroscience right now, in which the models that we build, so as I mentioned, we've always built models of processes to try and understand them. But the models that we build in Neuro-AI are not kind of like ones that we have built by hand to describe the process. Instead, they are themselves like deep learning models. And that approach has it's been controversial. One of the reasons it's been controversial is that, if you think about it, like your day job as a neuroscientist is to understand the brain. And, if your tool for understanding the brain is a deep neural network, deep neural networks, of course, are themselves like notoriously incomprehensible. So essentially this is what the critics would argue, what you might be perceived to be doing is to take one system we don't understand, which is the brain, and replace it with another system we don't understand, which is
right.
And so you've achieved absolutely nothing. So it's been somewhat controversial. Now, I personally don't agree that it has not. I do think it's been useful. And kind of like many of the advantages of Neuro-AI is what it's done is it's given us kind of a whole set of new analytic tools and theories and concepts and ideas for explaining like why the brain is so complicated. So basically, if you're interested in some kind of cognitive or perceptual function, like maybe you're interested in face recognition. So you want to know, how does the brain recognize faces? So one thing that people have done for about 4 decades is to stick electrodes into the brains of animals or humans where possible, and sort of look for neurons that respond to faces. And guess what? You can find neurons that respond to faces in the brain. So it's like, okay, job done. But it's actually not job done, right? Because just because you can find some neurons that respond to faces, that doesn't tell you anything about how they're letting you like recognize faces. It doesn't tell you that they're causally necessary for face perception, and so on and so on. And in fact, it turns out that when you find neurons that are sensitive to faces, you'll actually find that they're often sensitive to lots of other things as well. So, kind of you get neurons that are sensitive to faces, you get some that are sensitive to faces, but they're also sensitive to like, trees and guitars. And you're like, and then you find some neurons that are not sensitive to faces, but they're sensitive to lots of other things as well. And so, people came in with this idea that we could kind of build an atlas of the brain, right? We could be like, this is the face area, this is the tree area, this is the guitar area. And you could kind of build up a sort of like cartography, like a neural cartography.
Right.
And what we discovered is that, of course, if you only look for one thing, then you can find it and you can build that map. But actually, it's much more complicated. Actually, a sort of loose description of how the brain works is that everything responds to everything else in a kind of completely incomprehensible way. So, and people have a term for that. It's called mixed selectivity. It means that neurons are selective to lots and lots of different variables. So, this is a mystery. This is a puzzle. Everyone's like, oh my God, the brain is just so complicated. What can we do with this? But if you look at neural networks, then you can see that if you train neural networks to solve complex tasks, then neural networks, because neural networks don't have neurons, but they have units, which are sort of loosely equivalent to neurons, and you can see that in the training neural networks to perform complex tasks, exactly the same thing happens. So each unit, typically, rather than being specialized for a single variable like a face or a guitar or whatever, they will exhibit this property of mixed selectivity as well.
Right.
So we can see that both show like this complex coding. That doesn't tell you very much. It's like, okay, both are really complicated. Well, now we just know that now we've got two problems rather than one. But it turns out that in the neural network, you have the opportunity to do some really cool analyses. So rather than just looking at what each neuron does and say, this is a face neuron or this is a guitar neuron, what you can actually do is you can take a whole population of neurons. So now you've got this very like high dimensional signal, high dimensional because you can think of each neuron as being like a dimension, and there's lots of them. So it's high dimensional. And what you can do is you can find very, very clever ways to like visualize that the population activity by kind of reducing the dimensionality and plotting what's called the manifold. That's the manifold. So that's like the shape or the contour of the activity in a lower dimensional space. And by doing this, you can find that actually, although that population activity, although it looks super incomprehensible, actually it has kind of like really kind of like well-behaved and interpretable form on this like low dimensional manifold. So armed with this idea, people in Neuro-AI have gone back to the human, to animal brains or even the human brain, and they have done the same thing. So they've looked for these manifolds, and now this has become like a huge kind of like a huge industry within like neuroscience. Lots and lots of studies describe neural activity in this way, and it's been really, really useful. The identification of these kind of neural manifolds in biological systems too. So basically, Neuro-AI, although it has replaced one kind of like really difficult to understand system with another, it's not impossible to understand. In fact, there are ways that you can understand neural networks. And it turns out that the tools that you use for understanding neural networks are also really useful in neuroscience. And that's led us to like a really exciting place right now in the field.
Awesome. That's so cool. You're so good at explaining these things. So a neural manifold is a data abstraction, and we have manifolds for almost every state that the brain can represent. So we might have a manifold that represents happiness, a manifold that represents anger, fear, different processes of cognition, of intelligence. And the manifold basically plots this high dimensional space that if you were to look at the brain and take an instance of happiness, it could be plotted on this happiness manifold. Is that sort of roughly correct?
It would probably be easier it is roughly correct. It would be easier to explain if we use a simpler example. So, kind of like faces, let's stick with faces. Faces have lots and lots of dimensions. So faces can be happy or sad. Well, so we're back with your happiness example. Faces can be happy or sad. Faces can be old or young, for example, right? And so, kind of like if you look at the facial expressions, if you look at the expressions on a face, then you can describe them in lots and lots of dimensions because faces move in really, really complex ways. The musculature varies in very, very complex ways to express happiness versus, smiling versus frowning, or, kind of like the contours of old and young faces are like, they're different in multiple different complex ways. But if you look at the level of neurons, then what you'll see is if you present a neuronal population, a population of neurons in, for example, in visual cortex, with lots and lots of faces that vary from old to young and happy to sad, then rather than representing the detail of like how each face is in terms of how it looks in all of its kind of like, the variation of individual muscles or contours or shapes or whatever, you will find that what that neuron typically represents is a position. This is an example, but a position in like a two-dimensional space in which you imagine a two-dimensional space. The x-axis is how happy the face is. X-axis is how happy the face is, and y-axis is like how old the face is. So, kind of like an old happy face would be up here and a young sad face would be down here and so on. And like that manifold it's a representation not of what one neuron is doing, it's a representation of what the whole population is doing. And what that means is that the overall population activity in that population, although it's arbitrary and really, really hard to understand for any one object, it means that if you have two people whose age and happiness level is kind of similar, they, even if their faces look quite different on the manifold, they'll lie quite close together. So that means the population will exhibit an activity which is pretty similar in those two cases.
Right.
And that's, of course, very, very useful, because if what you care about, if those are the two variables that you care about, right? So, let's say that old, happy people are very likely to give you sweets, then it's really important to know, it's really important to represent the face in that frame of reference.
Right.
So mapping onto that frame of reference is something that we do naturally, partly because of the physical characteristics of the face and the information processing steps that go to just through like the way that visual information is transduced, but also because of what we've learned about the world. So, the dimensions of this manifold tend to represent things that are biologically relevant, like, age and, affect, happiness versus sadness. These are like super important variables for us biologically.
Yeah. So cool. How has neuroscience benefited from the last 4 years of explosion? Like, we've seen language models improve thousands of fold, playing with
Yeah.
the image generators in the last 2-3 days. I'm sure you've seen, just for some reason, what seems like a categorical improvement in image generators now, where they can do full, pieces of speech, where if you tried to get it to say your name in the past, it would just come out like a incoherent blob. Now it can do full scientific diagrams. I am
Imagen, yeah.
Yeah.
Yeah. So so incidentally, the reason that is true is because it's the large model that's generating the image, whereas previously the large model just called a separate tool. So previously, like if you asked GPT-4 to generate an image, it would call DALL-E 3, which is like a separate standalone tool, which doesn't have the 1.7 trillion parameters or whatever that.
Okay. I didn't know because it seemed like like in the past, it was always like stepwise improvement. It was always kind of continuous, and you got some big categorical shifts when they release a new model. But image generation, it almost feels like a different product now. But my point was,
it is a different product.
yeah, it's cool. It's so cool. It's amazing for education. How is neuroscience, or has neuroscience benefited from that? Have we been able to throw, a lot of EEG data, or, some sort of neuroscience data point into the massive amount of data centers that we have now? And has that spit out anything fascinating about the brain?
Yeah. That's a really good question, actually. It's a really good challenge for us in neuroscience. I actually think, I may have colleagues who disagree, but I actually think that we have not in neuroscience, the dial hasn't actually been shifted much by the kind of ChatGPT revolution. There's a few reasons for that. So one is that, these models are just so huge that it's actually, it's pretty difficult to kind of really understand what they're doing. It's always easier to understand like smaller, even if they're machine learning models, right? Deep learning models, like to understand smaller models. So, there has been stuff like in the field of language, people have done things like they've looked at the patterns of activation that you get in language models when, kind of people are reading sentences, or the model is reading a sentence, and they've used that to predict human brain activity, and you can show that it does predict human brain activity. In a way, that's kind of cool, but in a way, it also just tells you that the brain was very good at predicting the next word, which the human brain, which we kind of knew already, because you can ask people and they can do it. So there's a lot of pretty pictures being generated, but I'm not sure it's really changed the way we think dramatically about anything.
Yeah, that's kind of my point. I was curious,
Yeah.
where that development came. If you could click your fingers or send Demis Hassabis a quick text and be like, lend me, a country's worth of data centers to run a few Neuro-AI models, what would you do with that? How would you wave that wand? And, what kind of data would you throw at it? What sort of things do you think you could get if you had money wasn't an issue?
Yeah. I mean, kind of like in terms of application, I mean, I'm going to scope your question to like basic science, because if you're talking about applications, then there's a trillion things you could do.
Yes.
But like if we're just thinking about basic science, like the project of understanding the brain, I I think people are quite divided. So I definitely have colleagues who would be like, well, the answer is that we could build very large scale simulations that would try to replicate the sorts of complex behaviors that animals can produce and that we're really, really interested in.
Right.
Um, I, maybe it's just my lack of imagination, but I actually struggle to see what we would really get out of that. I mean, I have no doubt that if we had very large data sets, if we have very large data sets of behavior and you point foundation models at them, then you can train them to predict the structure in that data. I mean, the models just work, and they'll work on biological data just like they work on text and images and code and everything else. But I'm not actually sure how that would really meaningfully advance our understanding. I think, just because we can predict doesn't mean we can explain.
I wonder, could you get drug response sort of curves? If you were able to monitor the pharmacological response of some sort of drug under a dose, just with a massive data set, you might get some interesting data on how people could respond to treatments.
Yeah, I mean, like I said, if you're talking about applications, then there's lots and lots of applications that you can use. Being able to predict stuff is really useful in applications, right? That's why deep learning is amazing. So, translational applications, there are trillions. But, if your goal is just to explain and understand, then I think it's a bit harder. I actually have, I have a good friend and colleague who's, he's built a foundation model, or him and many colleagues have built a foundation model for psychology. So the idea is lots and lots of psychology data, so sort of rows of descriptions of experiments and then results, and responses, and trained it on many millions of rows of data. And the idea being that if you've got a good description of an experiment and how people behave, and you've got lots and lots of data like that, then you could feed in a new experiment, and model can predict what people are going to do, even if you haven't run that experiment yet.
That's so weird. That's so strange. And you're just feeding in completely different psychological experiments. So one could be related to one thing and one could be complete. It seems like that would have a trouble generalizing because it could just be completely different. But I guess with enough data, you get there.
Well,
that's so strange.
That's what we've learned, right? So, language, that's exactly the critique which was leveled at language, right? It's like, well, but language is infinitely generative, and like every sentence is different from every other sentence. So how could you possibly, by training on a finite set of sentences, build a model that could generate like realistically new sentences, at least that were like meaningfully and syntactically valid? And everyone's like, you could never do that. No. And then, they were wrong. And so, I think that it is feasible, if you had the right data, that you could do something like this in psychology. I actually think that and there's this paper which this foundation model for psychology which came out which purports to do this. I think it's reasonably limited. It's first stab, but I think it's a great effort. No doubt it'll get better with more data. I think I mean, what could we actually do with that? The question is, what do you actually do with that? And I think one way of thinking about what foundation models for big data in psychology or neuroscience could give us is they could give us a kind of like a standard model. So how, I'm not a physicist, so I probably garble this, but in physics they have like the standard model, and results are really interesting if they challenge the standard model, because everyone believes the standard model, and then or most people do. And then if you, kind of like, if you're able to find convincing evidence that it's wrong, then you've made demonstrable progress.
Yeah.
At least that's how I understand it. So imagine, we don't have that in psychology and neuroscience. We don't have a kind of standard model. But you could imagine that if you build this sort of foundation model, it becomes the standard model, and it predicts, what you should get based on our current understanding. You should get this, you should get that. Then if you find a new result, which is different from what the model predicts, then it's like, whoa, okay, well, now I've actually found something that's really quite new, and we need to update our thinking. So we would have I think we as experimenters, we kind of carry around what we think the standard model is sort of in our head, but it's like, it's not articulated. It's like, I see a study where they have an easy condition and a hard condition, and lo and behold, people are worse in the hard condition. I'm like, well, duh, it was harder. So that's the standard model, right? But like, it's a very boring one. So I think the foundation models could give us like a more nuanced standard model, perhaps.
That's such a cool idea, because I think you do hear a critique in biology that it doesn't have many grand unifying theories. That we have evolution, which makes a lot of claims and is a very solid theory. We have some theories in genetics, but biology as a whole hasn't advanced an incredible amount, and we don't have many great grand theories that are really testable, prove things that we can test things against. I am so building these foundational models. It sounds really cool. I didn't even think that you could just shove loads of psychology experiments into a model and that would generalize at all. It seems to that kind of breaks my intuition a bit, which is commonly happens at the moment, which is very fun. Um, a common critique of these language models is that they're not understanding what they're outputting. What would it mean for the model to understand its output?
I mean, that is not a scientific question. That is a sort of philosophical question. So, we don't have definitions in psychology of what it means to understand something. It's a sort of word that we invoke. There's no kind of like psychology of understanding, right? You
Yeah,
can't open a textbook. You can open books on the philosophy of understanding, and there's lots of kind of like discussion of what the difference between grasping something and understanding something and comprehending something might be, and of course all based on like English like meaning definitions of those words. Um, but in psychology, we don't have that definition. So people interpret it in different ways. Some people think that understanding means like being able to reference language to something which is in the physical world. So some people think that equate understanding, like if I understand what it means to like play tennis, then it means that I have a model of what playing tennis is that involves like the physical movement of the ball and the colors and all of the sensory data that goes with that. And some people say, well, language models, at least prior to multimodal models, they don't have access to that, so they could never really understand, because by definition they've like never seen a tennis ball or a tennis racket, so they don't know what tennis is. um, I mean, like I said, this is a philosophical or like a semantic issue. If you want to define understanding like that, then you can, and then that would be correct. um, I mean, there are basically other ways of thinking about understanding that have to do with like strong forms of generalization. So
yeah,
something that can, if you present me with A and B, that the idea that A and B go together and the idea that B and C go together, then understanding relates to the inference that kind of A and C must also go together to some extent, because they're linked by virtue of B. And that's a different definition. You could make that definition, and if you chose that definition, then language models clearly do understand, uh,
yeah.
because they're clearly able to make those sorts of inferences just like we are. So I think in a way it's not all that meaningful a question, although it is one that gets people very hot under the collar.
Yeah, I'm kind of curious on why people are so confident that it doesn't understand. I mean, one factor that I always play when if I think somebody understands a concept, it's always, can they explain it in different ways? Can they explain it in simple language? And something that language models are incredible at is that they'll tell you 100 ways of understanding one concept, and they will analogize until the sun comes down, and they'll continue to pump out new analogies. So there seems to be some underlying abstraction, some underlying understanding that it does have, because then it's able to generate all of these different, as someone who's trying to, I think it's the best education tool that's ever been released. I love it for learning new things. And I will just constantly be like, give me another analogy. Explain it to me like I'm 12. Explain it to me like I'm 5. Explain it to me like I'm 18. And it's phenomenal at that.
Yeah.
And that to me does indicate some level of understanding, because it can keep going lower. It can keep explaining it at a different concept. I understand the idea that it's not connected to the real world and it doesn't have that YX feedback loop of hitting the tennis ball or seeing the thing in real space, but it seems to grasp deep levels of what the content structures are.
Yep, that's absolutely right. Yeah, and kind of like I agree with that statement. And if you want to define understanding that way, then it definitely does understand. Just as a caveat, of course, kind of like skeptics, when presented with the sort of evidence that you just gave, they say, well, the model is trained on a lot of data and it's just kind of regurgitating that data. So, you said, oh, it can explain it like it's 5. So there's a subreddit, as you probably know, called ELI5, which is like the models are all trained on, which is like, kind of like lots of simple explanations of things. So, some people have said, well, the model is just doing a sort of clever version of cut and paste. That data is all there in its training, and it's just sort of regurgitating it at the right time. I think that's not true. I think the models are really capable of like piecing two independent things together to produce something that's demonstrably not in the training set, and there's lots of evidence for that. in the literature.
Yeah.
Um, but that is a common pushback that you hear.
Yeah, makes complete sense. You've mentioned multimodal a couple of times. What's the implication of a model? I think I read a tweet or an X, whatever you call it, where someone says GPT-5 will be multimodal. What are the implications of multimodal, a model?
Well, so our models are already multimodal. So multimodal just means that they deal with modalities more than other than text. So models that deal with images, video, or audio are multimodal models. So GB4 is a multimodal model because it has voice mode, so which can deal with audio, and it can, Sora can generate images, and like now ImageN, as we discussed, it was previously calling, a third-party kind of like application, but now it's generating the images itself as well. The implications of multimodal are that the model has access to much richer information. So there is clearly information that is present in images of the world or videos of the world that is not present in text, and that will inevitably make the models more powerful. So like the future is clearly going to involve multimodal models. But yeah, but in limited form, they're already here.
Right. I wonder what the tweet was referring to then. I think he said fully multimodal. I think it was Gary Marcus, so a big, someone is relatively big in the AI space. But yeah, I wonder what exactly he was referring to with fully multimodal.
Couldn't tell you.
Do you think we're yet to see big breakthroughs with AlphaFold? I'm really interested in AlphaFold. Can you explain AlphaFold and kind of what impact you think that will have?
Yeah, this isn't really my expertise, so probably not very well. I mean, AlphaFold is a machine learning tool which was deployed to solve an age-old problem, which is like to predict the way that proteins fold. This is a problem which structural biologists have been working on for a long time, and they've been building sort of handcrafted model, doing painstaking wet lab experiments, and then kind of like building, relatively models with relatively low numbers of parameters to try and predict kind of like general purpose rules for how these models fold. In a way, it's very much like language, right? So, the rules of protein folding are a bit like the syntax, and the proteins themselves are like the words with their different meaning, the semantics, and what you want is a sort of general purpose set of rules that you can then apply to kind of new proteins, kind of that you haven't encountered before. So I actually don't know a great deal about how AlphaFold works. I'm sure there are others who know much more than me, but what are its implications? I can tell you only what I know from reading the paper, which is, kind of protein folding is important for a number of possible number of domains. I think two, which are often talked about, are drug design, obviously. So, really important to understand how proteins fold if you want to design drugs. Also, I believe for various forms of like environmental kind of intervention. So, kind of like designing, I believe, bacteria which can kind of like consume plastics. That's one avenue, although I'm far from being an expert about this.
Yeah, those are the two that you hear most frequently. I think the drug receptor interactions makes sort of a lot of sense. As a drug interacting with the body is literally just two proteins doing a lock and key. So if you can just run that calculation many times, and then you get into David Baker's stuff, which is the artificial protein design, which I think gets very weird and very strange and could have very weird implications in 10 years' time if we're designing tiny molecular machines that do completely new things, novel things in the body. That's also scary and fascinating and interesting in lots of weird ways.
Yeah.
Is there anything that you're cautious about with AI? I know you're on AI safety boards, and this is something that you surely have thought about. How do you think about AI safety and AI provisions?
Yeah, so I'm cautious about everything. So I work for the UK AI Security Institute, and that is it's a part of government who is really like set up like a kind of startup within government, and it's on a mission to equip government with an understanding of what AI is all about, and in particular to allow them to anticipate the risks that AI presents. So, what risks does AI present? Well, lots and lots of risks. So, generally, you can divide the risks into those that are kind of like due to deliberate misuse and those that are inadvertent. If we think about deliberate misuse, you can think of three domains which are particularly important. So people might use generative AI systems or AI systems in general to help them commit crimes, and that's already happening, particularly around like financial fraud. Also, like very sadly, like lots of kind of like lots of misuse in the space of like child sexual abuse material because of the image generation capabilities of these models. Other forms of misuse include like what are often called CBRN risks. So this is the use of models to like obtain knowledge that could be used for committing terrorist acts with biological or chemical agents. And lots of concern around that. Lastly, cybersecurity, use of models for cyber attacks. I think it's probably fair to say that in those latter two domains, we haven't seen anything like really catastrophic yet, thankfully. But that doesn't mean that it couldn't happen. So lots and lots of safety work going to try and understand how we can safeguard the models so they can't be used for those purposes. So that's misuse. There's also inadvertent risks. Those fall into two categories. So one is that the models themselves, because they're very powerful, we might lose control of the models. So that means that, like embedded in a particular domain, and trained to do a particular task, the models might do things that we didn't anticipate. And, kind of that risk, people have varying pictures of what that risk entails. Some of them quite lurid and sci-fi, and others sort of more prosaic and grounded in, kind of like other ways that technology has, kind of like run under its own steam and robbed us of our agency. So yeah, loss of control risks are a real concern. And then there's this sort of wider set of societal implications for AI. Those AI is penetrating every sector at pace. It's going to continue to do so, and with new advances, it's going to do so in ever more kind of like intricate and powerful ways. But a few risks that are saliently highlighted are ways in which AI can exacerbate existing inequalities in our society. For example, by perpetuating biases that already exist. Ways in which it could disrupt our economy or labor markets, for example, by leading to large-scale disemployment through worker replacement. Yeah, there are many other societal risks. I won't enumerate them all, but yeah. I think
Incredibly well detailed answer. Most of the time, people are just like, "Yeah, AI drones are going to be a bad thing." That was a very well checklist
military
answer.
applications are also a concern, and
Yes, I'm sure.
Yeah.
Where do you stand on the runaway AI model type narrative? How? I mean, you're always dealing with unknowns because it's in the future, so we just don't know. But like, what might that scenario look like? What would a model need to be given hypothetically for it to give it that sentience, consciousness? I know those are words with a lot of baggage on them, but what's involved in that scenario? And do you believe that it's possible?
Well, so first of all, I think that there's a lot of our ways of thinking about this scenario have been sort of inherited from sci-fi movies,
Right.
and we should be cautious of telling like simple or naive stories about what that loss of control might mean. But that doesn't mean that it's not a concern. So the models are extremely powerful. They're capable of pursuing goals that we set them with like astonishing feats of reasoning. And that always raises the possibility that by attempting to reason about how to solve one problem, they might choose another goal, or they might choose like a sub goal that they think is important in order to solve the task that they've been set. And kind of in pursuit of that sub goal, there might be that might lead to all kinds of unanticipated, like harmful or undesirable outcomes that people don't want. So, what does that actually look like in practice? Like, I think a lot of people don't really know. One way of looking at it that we often talk about, like I said, is that, the model sort of kind of wakes up and is like, oh, look, I'm here in this sandbox or this computer. How do I get out of here? Personally, I think it's relatively unlikely that kind of volition, the volition will spontaneously emerge just because the models are big and powerful. What I think is much more likely is that because AI is a tool which increases productivity and efficiency and like helps us get stuff done quicker, we will choose to embed AI in structures which are indispensable to the functioning of society. And in the process of so doing, we will delegate to it. We will delegate decisions, behaviors, which previously were the province exclusively of humans. And because we've delegated those decisions to the model, we also delegate oversight or control over how things happen in society. And through that delegation, we gradually lose control over how we organize ourselves in our collective interest.
Right.
And, kind of like, you think of right now, I grew up, I was born in the 70s, I grew up in the 80s, and in the 80s, there was no internet. And we all got by fine without the internet. Life was okay. But like today, imagine if we didn't have the internet, like literally it would be a catastrophe on global proportions, right? So the internet is a good thing, right? It's allowed, astonishing progress in communication and like everything else. But what we've become dependent on it. So I think what we should be anticipating is a world in which generative AI is sufficiently embedded in our workflows, in our ways of interacting with each other, in the management of our societies, our economies, even our political systems, that it's very hard to get rid of it, because doing so would be like getting rid of the internet. It would be like, almost we'd be sort of back to square one in many, many ways.
Right.
So that's what I'm worried about. And I think that, that risk becomes magnified when you understand that today we're in probably a sort of grace period in which AI systems, first of all, they're not that good. I mean, they're good at language, but they're not that good at doing stuff. They're not that good at taking actions. But soon they'll be able to take actions. And secondly, we're in a grace period in which the main form of interaction we have with AI is like human to AI, right? So, you talk to ChatGPT and it tells you useful stuff. Like that's the mode of interaction we're in right now. It's not very far-fetched to imagine a world in which the dominant mode of interaction is that AI talks to other AI systems. And at that point, what you start to have is not just, we've delegated our wishes, our goals, our plans to AI, but it's also pursuing them by interacting with other AI systems which have other goals delegated to them. And, kind of like very much as, you and I might make a plan to solve a problem in a particular way, the models then conspire to solve the problem in that way, in a way that of their own devising. And what that affords is an opportunity for the way the outcome to deviate very significantly from what the humans who trained or owned those models might have wanted in the first place.
Yeah, makes complete sense. I was speaking to Dr. Joe Pearson from Australia. He's writing a book about the impact that AI will have on society. And he brought up this shocking number about the amount of people that are in AI relationships now. Like he thinks AI intimacy and AI relationships will be like the next biggest TikTok. I think like incredible amounts of Asia is already in like AI relationships. Is this a problem that you've spent very much time thinking about? Because this is like, the societal outcomes of that in, even in the very imminent future, but even a few decades down the line seem pretty shocking to me and pretty dystopian.
Yeah, absolutely. So this is I think this is one of the absolute top line changes that we can expect to see is systems becoming more. Some people use the phrase socio-effective, so socio-effective alignment. So more socio-effective systems. This means systems that behave in more humans-like ways and imitate the sort of social and emotional behaviors that we display to each other. Those systems will become much more widespread. They're already pretty widespread in some quarters, as you mentioned. There's some shocking statistics around, kind of the web traffic to sites like Character AI, which have these kind of like AI partners, friends, or companions, whatever you want to call them. Why is that a bad thing? I mean, we might just think it's a bit icky, but then, maybe future generations will think differently. I think the real risk is around manipulation. So, kind of like, obviously, we are we're pretty inured at this stage to things like, large scale advertising.
Right.
Kind of, we're bombarded with people trying to persuade us things all the time. But like what we're responsive to is when there's someone that we feel we have a relationship with, someone we trust, recommends something to us. We're like, oh, okay, I will probably go along with that. And that's, of course, how, things like grooming, radicalization, forms of indoctrination. That's how all of this starts, is by kind of like, people with, malicious intent forming relationships with victims. Various scams, of course, like that too. And so
Good point.
I think we should be really concerned about that. And it's one of the main things that we're studying in my team in AC.
Interesting. Yeah, all the AI girlfriends in North Korea are preaching their love for Kim Jong Un, and the same thing in China with the Communist Party, and that is a pretty terrifying thing, especially where that seems to be where mass adoption is going on. That if these agents are controlled by an organization like a hostile government dictatorship, they can basically encode these agents with any sort of inductive biases to believe a particular thing, to erase a part of history, to there's almost no better way. Like, if we think about how indoctrinating, as you say, an advertisement is, imagine how convincing it will be when you form a real relationship, real in inverted commas, that might change, relationship with an agent who understands you on an emotional level and understands how to manipulate you and get you to do things you don't want. And if their agents are hackable, and
That's right. Yeah. So
sufficiently terrifying outcomes. Thanks for that.
people who make AI will have a lot of power, whether they are large corporations or governments. Yeah.
Yeah. Let's finish on a positive note. What are you most excited about in the area of neuroscience and AI? What's coming down the pipeline that makes you incredibly excited to work on, and that you think just could have a huge impact on the world?
Alignment. So I think the most exciting and important challenge we face right now is that we need to know how to build systems that are aligned to humans. And, I think there are narrow ways of thinking about that problem, which is like we need to sort of somehow build in human values, whatever those are, to our models. That's the typical way that people think about alignment. When I talk about alignment, I mean something much bigger. I mean that we need to build technology which is like fit for human purpose. That means technology which like actually serves our interests rather than the interests of the people who built it, us, the users, us, all of humanity. And that might mean things like, kind of understanding what really, kind of like what positive interaction with a technological platform, whether that's, the internet, social media, generative AI, or any other form of interaction with technology, what a positive interaction really looks like, how we can promote interactions that, for example, accelerate the way people learn, so people can learn more, can be better informed, so that, kind of like people have interactions that when they look back on them, they realize that those were positive or satisfying interactions, rather than looking back thinking that they wasted their time. I think we need to find like equilibria in which humans and machines can kind of coexist for, mutual benefit, like with models doing what they're supposed to do and the humans like reaping the benefits. This is, for me, the most exciting challenge right now, and it's particularly exciting because it's a challenge that spans the two disciplines which I've worked in, which is you need to know something about psychology and the brain, and you need to know something about machines. And so that's what we're working on right now.
Yeah, it's an awesome time to be in the field, as we were talking about before. It's something that I'm trying to figure out if I can leap into in any way, because it just seems so cool. All the different aspects. Chris, this has been so much fun. I love how eloquently and articulate you explain these complicated concepts, and they are difficult, but I think you're a really amazing scientific communicator. I really wanted to touch on AI education, loads of other things. I'll have to have you back for another conversation because I know we're running out of time. But Chris, it's been such a huge pleasure. I thought this was an amazingly fun conversation.
Thank you so much. And if you really liked how I communicated, then you can read my book, which is
Yeah.
called These Strange New Minds, and it's published by Penguin.
I will be honest, I'm about 50% through at the moment. I didn't get it the whole way, but I'll link it below. Everyone should read it. It's really amazing. It's written quite accessibly. I think you don't need to have a computer science degree to jump into it. And I'll link it below. I think everyone should read it. Thank you so much, Chris.
Thanks, Owen.
I hope you enjoyed that episode with Dr. Chris Summerfield. I think he's an absolute legend. I think he's an amazing scientific communicator. If you're still interested in more Neuro-AI, I have some great news because I've spoken to Dr. Tony Zador, who's trying to use AI to map the entire human brain. Or if you're interested in a different angle, Dr. Paul Cizek. We go through 750 million years of evolution of the brain, and he explains what we can learn from the brain about how to build AI systems. I couldn't recommend those episodes more. Click them right now. And as always, subscribe to the channel. Thank you so much, and I'll see you next time.